All right, radioactive decay. That sounds serious.
That's the next podcast in our nuclear chemistry section.
Nuclear. It's pronounced nuclear.
Whatever.
Radioactive decay is when a particle breaks down into other particles and it gives off different types of radiation. There's a bunch of different types of decay that go along with all of the different particles that we learned about in the last section. So
alpha decay is the first one we're going to take a look at, and alpha decay is what it sounds like. It's the something losing an alpha particle.
Why do you say losing?
Because it's decay.
Decay means given off. So write a nuclear equation showing the alpha emission of polonium-210. So we're going to write some equations here. This is really what we're worried about with the radioactive decay. It's going to be just like any other equation that we do with a balanced equation, except we need to use our isotope notation to show what's happening, because the atoms are actually going to change their masses and their numbers when they split apart. Polonium-210 means it has a mass of 210, and if I look on my periodic table, polonium has an atomic number of 84. If that's going to decay, it's going to break apart into an alpha particle and something else.
Okay, so the first thing we know is that an alpha particle exists as a product. So we're going to write that one down first, and then figure out what would be left of the polonium.
We do need to know what's left. This is what we're concerned with. If it goes through alpha decay, what's left? Now, the actual atom changes because the nucleus is changing. So you don't have to have a polonium on both sides, but we are balancing equations, so you have to have conservation of mass. The numbers need to add up. The masses and everything else on the same side on the right and the left of the arrow. So if I have a mass of 210 on one side,
so that would mean you need a mass of 210 on the right side.
I need a mass of 210 on the right side. If I have 84 protons on the left,
then we need 84 protons on the right.
There we go.
We've already got 4 for the mass on the right, excuse me.
So that leaves me with 206 remaining.
Okay.
So whatever my particle is over here, I don't know what's left yet, is going to have a mass of 206.
Yeah, because we can't tell what the particle is from the mass number. We need to know the number of protons, and we know we've got 2 protons on the product side, the right side.
Right,
already.
and I need 84 total, so that means I've got 82 left over. So I have a particle with a mass of 206. That doesn't tell me much. But 82 protons, that does tell me what it is. If you look on your periodic table,
so that's the atomic number.
You get your atomic number, and that's lead. So polonium, when it goes through alpha decay, gives off an alpha particle, turns into lead. Very good.
Awesome. And then we have beta decay, a lot like alpha decay, except in this case we're going to be giving off a beta particle.
Sounds pretty good. The only thing you have to watch out for in this one is the beta particle has a negative number in the atomic number category. So you have to watch your math. You're adding negative numbers. Write a nuclear equation showing the beta emission of carbon-14. So we'll do the same thing we did before. Carbon-14, that's the mass that I gave you in the isotope.
Carbon's atomic number is 6, so that will be the proton number. It's decaying and giving it off. So we know it's decaying with a beta particle or an electron, so we write the symbol for that, and now we have to determine what is left over after the beta particle leaves the carbon atom.
Okay, so let's just add up our numbers to make sure they add up the same on both sides. I have a mass of 14 on the left and 0 on the right so far, so it looks like I've got 14 still over there.
Right, so that didn't change. That's easy.
6 on the left, -1 on the right.
So
5.
What plus negative? Well, 5 plus -1 would be 4.
Oh, that'd be 4 because I'm adding a negative number. So you have to look at what the totals are. It means we have to go the other way. 7.
7 and -1 equals 6. So we're equal on both sides now. And element 7 is nitrogen. So it's just the atomic number. Find it on the periodic table.
So we're gaining a proton. We had 6 and now we have 7?
Right, so we're going up in the atomic number.
Okay, but I gave off an electron. If I gave off an electron, isn't that like becoming charged?
Well, you would think it is, but that's not really what's going on.
So where's that electron coming from?
Magic.
I don't think
that's
it's magic. Harry Potter is also fake. Superman, Harry Potter, they're both fake. That electron, it's not coming from a normal electron. It's not just like it gave off an electron. It's actually coming from the nucleus. So what happens is, this is how beta decay works. You have a neutron, and that neutron, which is in the nucleus, is going to break apart. It's going to give off a beta particle, and then what's left over? Well, if we do the math, you've got a mass of 1, and that means I have to have a charge of 1 on the bottom to get them to balance out so there's no charge. What particle has a mass of 1 and a charge of 1?
Ooh, I know this. A proton.
It's a proton. So this is really how beta decay works, if you're confused about the numbers getting bigger. It's really just a neutron inside the nucleus breaking apart to make a proton, so our proton number went up, and it gave off an electron. So it's not the same thing as giving off an electron from the electron cloud where it becomes charged. It's actually making an electron from the nucleus.
In a sense that beta decay is not the atom losing an electron. Electron capture is not really the atom gaining an electron either to become an ion.
This is nuclear chemistry, so this is all where the nucleus is actually changing into something else. It's not just adding an electron. Notice it says capture instead of decay. Capture means something is being added to it. And if we'd go the backwards of beta decay, when an atom captures an electron, what it does is that electron is going to combine with a proton to make what?
A neutron.
How do you know it's a neutron?
Because of what we just learned about electron decay.
It's the other way.
That a neutron is basically composed of an electron and a proton.
And if you add up the numbers to balance it, you get a mass of 1, and the positive charge from the proton, the negative charge of the electron cancel out. You get 1, 0, and that's the notation for a neutron. So it combines with a proton to make a neutron.
Okay, so we're actually going to take a look at the electron capture and how it is in an equation. So we're going to write a nuclear equation showing an atom of silver, 106.
So the mass is 106, which we gave you. That goes up top. Silver's atomic number, you have to look up on the periodic table, is 47.
So it's capturing an electron here, so we're going to add an electron.
Electron is 0, -1, or a beta particle, and it's adding it so it's on the left side. It is a reactant now. And let's add up the numbers to see what we get.
Okay, 106, that's great. 47 and -1 usually adds up to 46.
It is 46. Which one has an atomic number of 46?
PD, palladium.
Palladium. So the atomic number went down because the electron combined with the proton to make a neutron. So we have 1 less proton, 46. And the mass is the same because there's no mass difference. So this is our particle that we're trying to solve for.
All right, positron emission.
Emission, it's actually the exact same thing as decay. Emission means
it's giving off
Giving off.
a positron, right? So it's going to lose that from its original element.
So write an equation for the positron emission from a proton.
Proton, not an element. So it's 1, 1, lowercase p.
Lowercase p, that's my proton. And positron emission, so it's going to give off, at the end of the reaction, a positron. Positron, I can't remember the symbol for that one. Apparently Mr. DiGiacomo doesn't know it either.
Crickets.
Positron that's the positive electron. It looks, you can see it in the name, you can hear it. So my electron has no mass, but the positive electron has a positive 1 charge. And the same symbol of the E or the beta particle, either one. And there's going to be something else because my mass numbers don't equal out yet.
So the proton numbers on the bottom already are equal, so we know we have a 0 there.
Okay, so 1 plus 0 is 1.
And then what plus 0 on the right side would equal 1? Another 1.
1 it is.
How about
So
that?
which particle has a mass of 1 with no charge?
A neutron.
A neutron. I made a neutron. Artificial transmutation. This is the fun one.
Is this like what happened to the Teenage Mutant Ninja Turtles?
No, that was just regular mutation. This is transmutation.
Oh, that's DNA mutation.
Yeah, not quite the same thing. This is where you get particle accelerators, and you throw particles at the speed of light, and you smash them together to see what you get new isotopes.
That's kind of fun. I like doing that on the weekends, smashing particles together. It's an exciting thing to do.
Yeah, if you have a 17-mile-long nuclear accelerator.
Yeah, no big deal.
Or if the Terminator attacks you, you can turn it on, and apparently they will be attracted to the electromagnetic field in the particle accelerator.
Wow, that was an obscure movie reference.
Terminator
Not
3.
obscure movie, but...
In a particle accelerator, they smash together to form new isotopes. This is how we make new man-made elements that do not occur naturally. This is actually kind of a form of fusion, where you're putting two things together, smashing the nucleus together to get something else.
So this is how those scientists come up with those new elements, huh?
It is.
Oh.
In a particle accelerator. Cool. These equations get a little bit more complicated because there's just a little bit more to keep track of. So watch the wording very carefully. Curium-242 is formed from...
Oh, formed from. That means it's probably a product then.
That is a product.
Nice.
The collision of plutonium-239 and an alpha particle. So let's organize this a little bit. The plutonium is a reactant, and the alpha particle is a reactant. Those two things are going to collide to form the curium. Plutonium on the periodic table, Pu.
Well, that one stinks.
It's not too hard if you know it. I get what you did. I see what you did there. 94 with a mass of 239. That's plutonium. That is going to be smashed together with an alpha particle. You know the alpha particle is 4-2. And it's helium. And it's a nucleus. All these equations, again, they're kind of assuming that you have those basic nuclear particles memorized. You need to know off the top of your head what an alpha particle is. That's going to make these easier. Plutonium plus helium. You know that it's going to make curium because we told you that.
Yep, 242, curium.
And on the periodic table it says curium has a mass or a proton number of 96 and its symbol is Cm. Curium. So we're done.
Yep, it all adds up, right? Right?
You tell me.
239 plus 4?
No. No, something's wrong.
That's 242.
There's another particle.
The other particle.
Just because it's not listed does not mean you can forget about it. Do your math. The numbers on the left and the right have to add up. On the left here, 239 and 4. That gives me 243. But I only have 242 on the right. One left over.
All right, 1. Okay. And on the bottom, 94 plus 2 is 96, and that's what we have on the bottom already.
So there's no
this
protons.
Is clearly a 0, and a 1 over a 0, if I remember correctly from my previous podcast, that's a neutron.
That's the neutron. Don't forget about that second particle in these equations. Sometimes there's going to be multiple neutrons. Sometimes there's electrons, beta particles. Any number of things can be given off. Sometimes they're entirely different atoms. So pay attention to those. Calculate the numbers and figure out what is left over. That'll help you with this podcast.